Okay, hi everyone. This is the second video of the 7th week when we will briefly discuss the exercises that were included in homework 1 and what were the intended solutions. So let us move to exercise 1. So you were given two networks that both have 256 nodes and the average degree of 4. And the question was, by observing the networks, what can you say about their degree sequences and degree distributions? Now, firstly, regardless of the fact that the average degree of the networks is the same, their degree distribution can still, of course, differ. And since you know the number of nodes, the degree sequence and the degree distribution are actually equivalent. So if I give you a degree sequence, you can easily construct the degree distribution, and also you can take the values of the degree distribution and multiply them by the number of nodes, and you will have the number of nodes with particular degree, so you can back construct the degree sequence. So it's enough to reason only about one of these things. Now, looking at the pictures, the degree distributions of the networks are not the same. The left graph is an example of an Erdos-Renyi graph, whereas the right example is a network. It's a scale-free network generated by the Barabashi-Albert graph. So what will be the main difference between the networks? On the left-hand side, the degree distribution roughly follows a Poisson, so most of the nodes have very similar degree and there are no very high degree nodes. Whereas on the right-hand side, the degree distribution roughly follows a power law. So you get here in the center some very high degree nodes that you don't see on the left-hand side. So the main difference basically is that you get hubs or high degree nodes in the right network, but not in the left network. So the degree distribution of the left network is relatively homogeneous, whereas the degree distribution of the right network is relatively heterogeneous. I haven't yet looked at your results, however, I expect that at least some of you will reason about low degree nodes, so that you get nodes with degree 1 in the left network, but there are no such nodes in the right network, which is correct, because the right network was generated using the Barabashi-Albert model, where each new node that arrives would create, in this example, 2 links. So each node has degree at least 2. However, it is hard to reason about low degree nodes, because usually in a network there will be many, especially if a network has a power law degree distribution, so it's hard to see all of them. I was hoping that you will reason about the high degree nodes or hubs. They appear in the right hand side and they do not appear in the left hand side. So this is basically it regarding exercise 1. Now let's move to exercise 2, and I will move to the blackboard. Please look at that on your own. So assume that the exercise reads that you have a simple undirected network with m nodes, m links, and c connected components. And we were supposed to show that the following two equalities hold. So that n minus c is smaller than larger, or smaller or equal to n, which is smaller or equal to n minus c plus 1 over 2. For the first inequality, you were suggested to use mathematical induction. You can do an induction on either n, c, or m. I believe that the easiest case is to do the induction on m. So you first show the border case, which should be trivial. Then you assume that this equation holds for some particular network, and we will fix the number of nodes. And we will not make any assumption regarding n, so our proof will be a general proof for any such network. So let's assume that this inequality holds. Now I want to show that if I do an induction on m, the inductive step, when I increase m by 1, would the inequality still hold? And basically, if you have a network with C connected components, when you add another link, two things can happen. You can add a link within some connected component, so between the nodes that are already in the same connected component. So the m will stay the same, the C will stay the same, and m will increase by 1, so inequality obviously still holds. The other example would, the second example would be that you add a link between two nodes that are in different connected components. Now these two connected components connect, so there is only one connected component, so C will decrease by 1, but still, since m increases by 1, the inequality will still hold. So this is basically the case how you should prove the left inequality. Regarding the right one, the exercise says that you can use simple reasoning. An idea was here that, okay, so I have C connected components. Now, in order to get as many links as possible, obviously these components have to be full graphs or cliques of this network. Now, the only thing to still reason about is what is the size of these connected components. And you can easily see that the maximum in the number of links will be achieved in one of the extreme regimes. One example would be that you make all the components of the same size, which will be n over c. And the other option would be that you make one large connected component, which will include most of the nodes, and then you also have C minus 1 connected components that are that consist of individual nodes, so isolated nodes. So the number of nodes in this large connected component will be n minus c plus 1. And you can do a simple computation to realize that in this second scenario you will get more links. And this effectively proves the second inequality. Now, moving on, I mean, this was relatively trivial. The main part of the exercise was to use these two inequalities to derive a criterion that a network will surely be connected. So, let's have a connected network that has one connected component, obviously. Then this equality reads n minus 1 is smaller than n is smaller than n over 2. Now, so this is for C equal 1. Let's now have two connected components. The inequalities will then read n minus 2 is smaller than equal to n is smaller and equal to n minus 1 over 2. Now look at the right hand side and assume that the number of links is strictly larger than n minus 1 over 2. In that particular scenario, you can obviously not have two connected components because you have too many links. If you assume that the number of links is larger than n minus 1 over 2, you necessarily have just one connected component, so the network is surely connected. And this was the final criterion that you are expected to derive. And the exercise then asks, is this practically useful? Obviously not, because you demand to have an almost complete graph, and we know that real networks are sparse, so in practice this would be rarely used. I mean, for your network, you can always check whether this inequality holds, and then you can assume connectivity. However, this will be true only in an almost fully connected network, in a dense graph, which is not realistic for real networks. Okay, so this is regarding the second exercise. Now, if we move to the third exercise, let's look at it together. So the exercise talks about connectivity in directed networks. And it says that in labs we saw algorithm for finding connected components in undirected networks. So if you remember, we had some function, let's call it connected components or CC, which took our graph, the set of nodes that were not yet visited, and some node index for which we wanted to find its connected component. Now the first question reads, what would the same algorithm find in a directed network if one could follow the links in any direction? If you do that, obviously you will find weakly connected components in a directed network. So basically you're simply just ignoring the directions of the links. Now moving on, what would this algorithm find in a directed network if one could follow the links only in the proper direction? So you start with a single node, then using the depth first search routine of this function, you will follow the links in their proper direction. And so this is my node I. So what I will find is the so-called out component of node I. So the set of nodes from to which you can come from I, so there is a path from I to that particular node, following the links in the proper direction. Now, what would the same algorithm find if you follow the links in the opposite direction? With a similar figure, we can see that what will the algorithm find is the so-called in component of node I. So all the nodes from which you can come to I, so there is a path from that node to node I. And the intersection of the in and out components of one particular node is actually the strongly connected component of that node. So that you can reach all nodes and that all nodes can reach you. And based on these answers, you were supposed to come up with an efficient algorithm, again using depth first search, for finding strongly connected components in a network. So how would we do that is, let's add another parameter to our function, which will denote in which direction I am following the links. If this parameter is set to true, then I follow the links in the proper direction, and if this parameter is set to false, then I follow the links in the opposite direction. So if I first apply this algorithm to my network for some randomly selected node I, and set this parameter to true, what I will find is the out component of that node. Now, what I do next is I also want to find the in component to then take the intersection. So I can now again use this function with parameter false, so that I will follow the links in the opposite direction, which will effectively find the in component. However, in order to find the intersection or to find the strongly connected component, I don't again have to go through all the nodes, but I can only go through the nodes that were already found to be in the out component. Because if they are not in the out component, they obviously cannot be in the strongly connected component. So the second parameter should be now set to out. And this can make a big difference, because for some nodes you can immediately find that the out component, for instance, consists only of 7 nodes, whereas a network has 1 billion nodes. So in the second step, you will only traverse those 7 nodes instead of the entire network, the billion nodes. And what comes out is basically the strongly connected component of node I. The last step that you should not forget about is that, remember how we implemented this function, is that this set n consists of nodes that we have not yet visited, and once we find some connected component or I component or something like that, we remove these nodes from n. And in the second step, when we will start with out and get the strongly connected component, the nodes in the strongly connected component will be removed from this set out. However, some nodes may still remain. So nodes that are in the out component but are not in the strongly connected component. So at the end, you should correct your initial set n and add back the nodes that remained in this set out, so nodes that are in the out connected component and are not in the in connected component. And I believe that this is the most efficient way how to find strongly connected component in a network without having to do a lot of programming. Okay, so the network you were given was an email communication network from Enron, and you were supposed to compute the number of strongly connected components and size of the largest one. So the number of connected components that I get is 78,058, whereas the size of the largest connected component consists of roughly 10 or 11% of the nodes. So regardless of the fact that the average degree is larger than 1, we don't get one giant connected component as we would do, as we would get in an undirected network. The theory behind this is the emergence of a giant connected component in a random graph. And at the end, you were asked what is the reason that we are not getting one giant connected component, one giant strongly connected component, and there is no correct, probably no correct answer to this. There are only multiple answers. How I understand this is that since this is a communication network of some company, there will be some hierarchical structure there. So you have the boss, and that boss has some subordinates, and so on and so forth. And for instance, these are like different divisions of the company, which will be strongly connected components, and a boss will tell those people what to do. And then those people will further tell their employees what to do, and so on. So it's usually boss tells you what to do, you don't tell that to the boss. And based on this idea, I do not expect to have one large connected, strongly connected component, but many smaller ones. And there might be, so due to the hierarchical structure of most organizations. Of course, you can come up with even a better explanation of this. Okay, let's move on to exercise 4. So you were given a 2-star graph, where double star graph, where you have 2 nodes that connect between each other, and then a lot of green nodes that each green node connects to both of these gray nodes. And it's easy to see that the average clustering coefficient will go to 1, because each green node obviously has a local node clustering coefficient of 1. I mean, it only connects to 2 neighbors and they are connected. And since there are only 2 other nodes, the average over all nodes will go to 1. However, on the other hand, the network clustering coefficient, which is defined 3 times the number of triangles divided by the number of connected triplets, will go to 0. Why? Because each new green node that you add will create one triangle, but will create many connected triplets, something of the order of n, where n is the number of nodes in the network. So each green node will connect connected triplets to every other green node through these gray nodes. So you are expected to come up with a simple example of a network where you get the same property, where this average clustering coefficient and the network clustering coefficient differ. I expect that most of you will come with some examples like, instead of double star network, let's use a triple star network or something like that. There are also other simple graphs that would have the same property. One would, for instance, be a wheel graph that will look roughly like this. Another example would be a windmill graph, when I will just remove every second link here and so on. Hexagon graph will have the same properties and so on. And as I said in the class, that you are only interested here in the scaling, so you do not need exact computations for average clustering and the network clustering, as long as you show that one goes to 0 and the other goes to some constant that is strictly larger than 0. Okay, let's move on. In the next exercise, you were supposed to implement the function to find so-called effective diameter, which is a smoothed version of a regular diameter, and apply the algorithm to 3 citation networks that grow in time, see what their effective diameter is, and try to reason whether the results are surprising or not. The values that I get is, for the smallest network, it has 18,985 nodes, the average degree is 4.4, and the effective diameter is 27. We have discussed that there are multiple ways how to implement the effective diameter. This is the result for one of those ways. Then if we go to the next network, when we add papers from another year, from 2012, I get 38,356. The average degree is 5.7, and the diameter is 23. And the final network has 65,473 nodes. The average degree is 7.1, and the effective diameter that I get is around 21. Now, looking at these results, things should be roughly somewhat counterintuitive, because when the network grows, the effective diameter decreases. So, meaning that when the networks grow, they actually shrink. So, meaning we would normally expect that when a network grows, it grows like this. But it turns out when networks grow, they actually shrink and become denser and denser. Why is this the case? If you look at the paper that I cited in the exercise, you can actually show that if you have a network that is increasing in size and it's also densifying, meaning that the average degree is increasing, which is simply saying that the bibliographies of papers are getting longer and longer, which is a known fact. But if the network is densifying, and you assume that the degree distribution of a network is a power law, you can show that the distances between the nodes should shrink, so that the effective diameter would shrink. In the case of citation network, we can maybe also come with some intuitive explanation of this phenomena, which we don't know whether it is exactly true or not. So imagine that you already have some citation networks or citation network of papers when papers cite the other papers and they are on a certain distance, undirected distance. Now let's imagine that we publish a new survey paper, a review paper that reviews a certain field. It will probably review a lot of papers within this field, and for every pair of such papers, their distance will be now at most 2 because of this review paper or some encyclopedia or something like that. So unless the nodes were already connected before, this, in case they're of distance 1, in any other case, the distance between the nodes will now become 2, which can be only smaller or equal to their previous distance, so that the distances will decrease. So an important highlight of this exercise is to realize that most real networks, when they grow, their diameter will shrink, and this should come at least to some extent to be counterintuitive. Okay, let's move on. Exercise 2.1. It says that for an Erdos-Renyi graph, you need an efficient implementation of random selection of nodes, which can be efficiently implemented for almost any graph structure. However, in some other cases, like in the case of the Barabashi-Albert model, you need an efficient implementation of node selection by that degree, so that node I is selected with probability proportional to k sub I, and you can easily derive that that exact probability will be k sub I divided by 2n. Now, what would be a graph representation that will allow you to select nodes with this probability in constant time? Obviously, the answer is the edge list representation. So, in that case, you have an array or a list of edges. What you do, you randomly select one edge, which happens with probability m. You then randomly select one of its endpoints, which happens with probability, so endpoint will be selected with probability 1 over 2n, and since each node has the number, it appears as an endpoint, the number of times as its degree, we will get exactly what we want. I expect that at least some of you will submit a solution where you store the nodes in a list as many times as its degree, and then selecting an index out of this list will select the nodes proportional to their degree. However, as the exercise says, this is not a graph representation. This is not a network representation. You have to store that data structure next to your graph representation. So, I mean, you cannot construct a graph if I just give you the degree sequence. And final thing that I want to discuss is that maybe some of you came up with a solution that you have an adjacency list representation, and then you randomly select a node, and afterwards a random neighbor of that node. For the configuration model, we have shown that the degree distribution of a randomly selected neighbor will be the degree of the neighbor times the probability, the fraction of nodes with that kind of degree divided by the average degree. And since there are n sub k degree nodes, you can you should divide this by n sub k in order to get the probability that a particular node with degree k will be selected. And you can simplify this and you will get to the same equation that we want. However, I should highlight that this only holds for the configuration model where there are no correlations between the degrees of the nodes, because we constructed the graph completely at random. In real network, where there might be correlations between degrees of the nodes, which we will show in the next video, so-called node mixing by degree, this formula will not hold. Okay. Let's move on. So consider, next exercise reads, consider a random graph model in which links are placed independently between each pair of nodes with some probability that is proportional to the product of two v's, where v is some non-negative number associated with node v. So what we can write is that the probability of a link between nodes I and j is proportional to v sub I times v sub j. And if we want an equality here, what we should do is add another constant here. Let's call it large x times v sub I times v sub j. And we don't yet know this value of x. Now the exercise says is that first show that the expected node degree is proportional to the value associated to that node. So the expected degree of node I, how can I write this? I can sum up the probabilities of a link between node I to every other node. And if I sum up all these probabilities, I will get the expected number of links that will end at this node I, and this is simply the degree of the node. So this equals a sum from all j's of p sub ij, and I can plug in this formula, so I get the sum of all j's over all j's of x v sub I v sub j. And notice that this sum, these first two terms do not depend on j, so I can put them out. So it's x times v sub I. And finally, what I'm left with is the sum of the values v over all nodes, which is some constant, and I will denote that constant with large V. So we have already proven that the expected degree is proportional to V sub I, and there are also some constants there. Now, next, the exercise wants you to come up with an exact expression for P sub ij in terms of node degree sequence. So what else I can do is that know that if I sum all P sub j's through all possible pairs of I and j, I will basically sum the values of the adjacency matrix, which will be in the undirected graph twice the number of links. Now I can again plug in the value for P sub ij, so I get sum of x v sub I v sub j. Let me replace these v's with their degrees. So I get the sum over I sub j, then x copies. V sub I will be k sub I will forget about this expected value here, will be k sub I divided by x times v, and the same for the second node. So x times v. So what I am left with is the sum through all ij, the product of their degrees, divided by the x times v squared. Now I can split this sum of the over I and j into two sums over I and over j. I evaluate them separately. So the first sum over I will simply sum all the degrees of the nodes, which will be twice times n, and the same for the second sum. So what I will get, the top part will give me 4 times n squared, and the bottom part will give me x times v squared. Now, looking at these two things, you can immediately see that, let me write this here, you see that? Yeah. Let me write this here, so twice the number of links is x times v squared, so some constant. Now we move back to the top formula, which is the one that we actually want to derive. I can plug in these values here, so it's x times k sub I divided by xv times k sub j divided by xv. One of the x's cancels, the other one is x, the bottom part now equals to 2n, so what I get, k sub I, k sub j divided by 2n, which is the final result. If you want, you can also write this bottom part as simply the sum of the degrees of the nodes, so the formula really just includes the degrees of the nodes. And so this was just some simple mathematical derivation. The main part of the exercise was this last part that says discuss the result. And what you should see is that what we got is a probability of a link in the configuration model that we have discussed in lectures. Meaning that so in the configuration model we said, okay, let's fix the degrees of the nodes and then connect the nodes proportional, the probability of a link between two nodes should be proportional to the product of their degrees. But then one could think of, okay, instead of degrees, what if I come up with some other values for each node, maybe some external values, and I connect the nodes proportional with a probability proportional to the products of these two numbers. It turns out that these numbers are effectively the expected node degrees. So no matter how you call these v's, these are actually the expected degrees of the node. And once again, so if we assume that the link will be formed with a probability proportional to the product of some values associated with nodes, there is just one such model, and that model is called a configuration model. Of course, the entire thing will change if I connect the nodes with probability proportional maybe to the sum of these values or something else. But if you assume a multiplication, then there is just one such model, the model that we have discussed, which is called the configuration model. Okay, let's move on. How are we with space? Let's try to be quick. The next exercise gives you some small social network, and you should plot its degree distribution. How this degree distribution will probably look like is, so we have k, b sub k. I would expect that it will follow a straight line on a doubly logarithmic plot. Then you are also supposed to construct a random graph with the same average degree, and the random graph has a Poisson degree distribution that would look something like that. Then you should superimpose the theoretical Poisson distribution on this plot with a straight line, which would roughly follow these dots for the Erdos-Rényi graph. And finally, you are supposed to implement the Barabashi-Albert model that we discussed in one of the previous lectures, and construct such a random graph and plot its degree distribution, and it should follow a straight line with the exponent, with the gamma exponent equal to 3, so you will get a power law degree distribution. Apparently, I will have to stop here and make another video. Sorry for that.